Hello, I'm Matthew Lay, and today we are going to study electrical current. Let's get started. We have some objectives for this lesson. First, we want to define electrical current flow. Then we want to understand the concept of current flow and what makes it possible. And finally, we're going to calculate the current in a circuit, given a quantity of charge and the amount of time it took for that charge to pass by a given point. So let's look deeper at electrical current. What is electrical current? Simply stated, electrical current is the flow of electrons within an electrical circuit. So we're going to look at that at a physical level and look at some animations since this is physically invisible to us. We have some animations in this presentation to highlight what actually is physically happening. We're going to go back to our flashlight example that we had previously in an earlier lesson. And just to review, we have an incandescent light bulb, which is touching the top of the positive terminal of one battery. The negative terminal of that battery is connected to the positive terminal of the second battery, and then the negative terminal comes through a wire through a knife switch here, which is currently open, but when closed, we'll have a completed path back to our incandescent light bulb. What we want to do is bisect this wire down here and look at what's happening internally. So here is a bisection of that wire, and this outer shell is the insulation, the red portion. That's our outer insulation, which no current will flow through, but this inner golden color is our copper core. So what I'm trying to depict here is a wire that's been cut in half, right down the middle, and so we're looking at it, what's happening internally. And then these little spheres with the letter E are the copper electrons, and we know from earlier study that the electrons are what is actually freely given up by an atom and makes electricity possible. So if we have a wire and the negative side, this would be the bottom of the battery, the bottom of my circuit, my flashlight is on the negative side of my power source, and to the right here is the positive side of my power source. We know that our electrons are negative in charge, and because we know that opposites attract from an earlier lesson that we had, that our negative electrons are going to be attracted towards the positive side of our source. So these electrons in a completed circuit are going to be moving within the wire, and they're going to be moving from the negative side of the source to the positive side of the source. Let's see how we can actually measure this, because we're going to explore a multimeter, a volt-ohm meter, some people call it. Multimeter means it has multiple functions. One of the functions would be to measure amperage. We're gonna learn what amperage is here in a moment. But if I just pick a point on the wire and I count electrons as they go by, and I'm also denoting the time in which I am counting these. And if I have a certain amount go by in a certain amount of time, I can calculate the current flow that happens in that wire. So let's look at how we do that. In measuring this, we are actually benefiting from the study of a French scientist. His name was André-Marie Ampère, and for his name is where we get the units for our current measurement. We do know that 6.242 times 10 to the 18th electrons equals 1 coulomb. Now, electrical current, as defined by our System International units, is 1 unit of current is equal to an entire coulomb, or that many electrons, passing by a reference point in 1 second. Current is measured in amperes, and that was a honorary thing given to Ampere, this scientist Ampere, for his study on the measurement of electrical current. So our equation then is 1 ampere, or 1 amp. We always shorten ampere because it's a long word. 1 amp equals 1 coulomb in 1 second. We know from a previous lesson that we're actually going to represent the quantity of amps in mathematical formulas with a different letter from the units. And this letter for current is I. Of course, we couldn't use C because we've already used C for coulomb for units. So the letter I, a good way to think about it is in the intensity of the current. If you would actually ever get shocked, what you actually feel is an intense feeling, and it's actually the current that's moving through your body is what you're feeling. So that's how I can remember that the letter I stands for current, or the intensity of the electricity. So we're going to use the letter I to represent current in our math formulas. So let's look at a particular math formula. So electrical current, restated, is the flow of electrons in an electrical circuit. Electrical current, we now know, is measured in amperes, which we always shorten to the word amps, and we use the letter A as the unit after our quantity. In formulas, the current will be represented by that letter I. So here's our formula. If you remember from our previous lesson on electrical charge, Q is the letter used in formulas to represent electrical charge. Now remember, Q is measured in coulombs. And I'm also introducing a new letter here, lowercase t, we're going to represent throughout the course as our unit of time. So I is our current in amps, Q is our charge in coulombs, and T is our time. And in this case, our increment of time is going to be seconds. It's not always seconds in our formulas, but in this particular formula, it is going to be in seconds. So electrical current, let's look at a sample. If we had our reference point here, and we're counting per second that we have 8.134 times 10 to the 16th electrons moving by that reference point every second. What would that calculate to in amperes or amps? Well, we know that 1 coulomb is 6.242 times 10 to the 18th electrons. And what I've done here is I wanted to simplify our math problem. Since we have times 10 to the 16th here, and we have 10 times 10 to the 18th here, we have different magnitudes for our numbers. I took this number and I converted it so it's the same magnitude, and in doing so, 10 to the 18th over 10 to the 18th is just going to cancel out as 1, and it kind of simplifies our formula. We're going to see that here in the next line. So because I got to the same magnitude by just moving the decimal point, I can simplify our fraction by just saying 0.08134 divided by 6.242. And that gives us 0.013 amps. Now we know from our engineering and scientific notation lesson that we don't quantify something like this in engineering notation. We want 1 to 3 positions to the left of the decimal point. So I need to move that decimal point, and for engineering notation is how we're going to represent all of our numbers moving forward. We want to move that decimal point 3 places to the right, or times 10 to the negative 3, and that is going to give us our engineering prefix of milli, which we're just going to use the lowercase m. So our current flow is going to be 13 milliamps. So there it is on our ammeter. A meter that measures amps, we simplify and just call an ammeter. And so here, this is an old school dial ammeter. Of course, we're going to be using digital ammeters in this course. But the current flow equals 13 milliamps, and the milli gives us a certain magnitude or how large or small that number is. And that's why we introduced engineering and scientific notation to you in an earlier lesson. Okay, so an ammeter measures this current within our simple flashlight circuit here. So anytime I use the term ammeter, I'm talking about a meter that measures amperage or amps. And there's our 13 milliamps for our flashlight, which is a pretty appropriate quantity for something like a flashlight. It's that low of current. A light bulb doesn't really take that much current. And that's why if used properly, the batteries last for a long time. Okay, let's review. Define electrical current flow. And like we did in the previous lesson, let's pause, think to yourself, and then come back to see the answer. Electrical current flow is the flow of electrons within an electrical circuit. We actually get the term electricity or electrical from electron because electrons are what actually move in the circuit, in an electrical circuit. Understand the concept of current flow and what makes it possible. Again, take a moment, think about that, and then come back. Electrons are the movers in the circuit, as we just previously stated, but it's also electrical charge that makes that movement. Remember from our earlier lesson, if a battery doesn't have that electrical charge inside of it, those coulombs of charge, it will not have any effect even in a closed circuit. We need the charge as well as we need the closed circuit for the movement to actually happen. Dead batteries can't create electron movement. Calculate the current in a circuit given a quantity of charge and the time factor. So here is our given example. If the electrical charge is 3.6 coulombs moving at a rate of 2 seconds, what is our electrical current? So again, pause the video, calculate that out, and then come back. Okay, our formula is for current. Remember, I represents current, Q represents our electrical charge, and T is our time, in this case in seconds. So our given was for Q would be 3.6 coulombs, because coulombs is a unit of charge, and Q is our measurement of charge. And 2 seconds, our increment of time is seconds, and 2 was the given time. If we take 3.6 coulombs and divide it by 2 seconds, we're going to get 1.8 amps. And that is the amount of electrical current we would have for that much charge moving over that period of time. So this concludes our study on electrical current. I hope that was helpful, and we shall see you in the next lesson.